Hi there. Let's make sure that you are getting started correctly on Part B of this number 6 investigative task. So next, does the statistical test that you completed in Part A provide evidence that this training is effective in improving a person's ability to predict coin toss outcomes? So it says, if yes, justify your answer. I'm going to tell you the answer is no. So it doesn't suggest whether or not there's any improvement regarding the prediction of coin toss outcomes because there is no aspect of comparison here. So if you want to have some idea of whether this training, which I'm suggesting is a sham, is fake, if you want some idea of whether the training is effective, then you need to have some aspect of comparison in terms of your test. You need to be looking at before and after scores. So in fact, you need to look at the difference between the number of correct predictions after training versus the number before training. So this is what we call a paired test. It is a t-test because we're going to look at a mean difference. So it's called a paired t-test in the sense that we are going to pair up the two outcomes for each subject. So subject number 1, after training, was able to correctly predict 61 out of 100 outcomes. Before training, they were able to correctly predict 46 of the 100 outcomes. So it looks like that the first subject actually did improve after training. You will notice, though, on your calculator, what you should do then is take the second list, you should subtract the first list from it, and then you can do a statistical test on those differences. Because what you're really interested in here, to answer this question, if you're interested in whether or not the training is effective in demonstrating an improvement in a person's ability to predict coin toss outcomes, you have to compare. So we're going to be looking at mean differences here. And as we've said in class a number of times, when you see mean differences, the null hypothesis value is often 0. So let's write the null and the alternative hypothesis here. A good idea to start by writing the parameter. So it's a little bit different, and the difference is important. It's a little bit different than what we wrote about in Part A. So here's what the parameter represents. Now mu is the mean difference in the number of correct I'll put it in quotes again, coin toss flip predictions. And we're going to look at after minus before training. So mu is now the mean difference in the number of correct coin toss flip predictions after training minus before training. So the null hypothesis here, and I often write this, since you've defined the parameter up here, you don't have to do this because you've defined it as a mean difference, but I often write mu diff. So just to remind myself that this is a difference. So if the training has no effect, if we have no mean difference, then there is no change, if you will, after training compared to what we saw before training. So this would suggest that the training has no effect. So if we are interested in showing an effect, then we're interested in a mean difference that in this case would be greater than 0. We took the after training scores and we subtracted the before training scores. So if this is a positive value, then the after training scores are higher. We are correctly predicting more outcomes after training than we are before training. So we're looking for a positive difference. In fact, you could subtract in the other direction, then your alternative hypothesis would be a negative difference. You could do it either way, it doesn't matter. So in terms of the calculator then, one of the things you do have to do is actually create your data. So stat enter, understand this is my before training data, this is my after training data. So you do need to create then another list. If you go to the home screen, the way that I've set up this hypothesis, you're going to have to take list 2 and subtract list 1. That's after minus before, and then store that into list 3. So notice here, then the first subject had an increase of 15, the next subject had an increase of 14, the next subject had an increase of 3, the next two subjects actually had fewer correct after training than before training. That's why those numbers are negative. So at this point, you have the null hypothesis, you have the alternative hypothesis. Now you want to check your conditions, your randomness, your independence, your normality condition. You should know how to check the normality condition on the calculator. You want to hit second y equals, and you're going to want to look at the histogram and the box and whisker plot, but you want to change this to list 3. And then if you're going to run the t-test using the data, make sure you select list 3. Otherwise, you need to do the one variable statistics for list 3 so that you can get your mean and your standard deviation to actually run the test on the calculator and write about it and interpret it in context. This, as I've been suggesting, this treatment is a sham treatment or a fake treatment, and you should notice then, no surprise, you're going to get a p-value that doesn't indicate significance at any of the standard levels, 1% or 5% or 10%. That should not be much of a surprise. We really shouldn't be able to improve someone's ability to predict the outcome of a coin toss, if you will. Hope this has been helpful.